So today we're going to discuss matrices. First, what is the definition of a matrix? A rectangular array of math objects such as numbers and functions and etc. etc. And let's do some examples of that. Let's say if I start with this is an example of a 2 by 3 matrix. So 2 rows and 3 columns. And it could be a matrix looking like that. If you look at this, I put in between brackets. That's another notation thing that we use with matrices. I could have a 2 by 3 matrix that looks like this. Or I can have a 2 by 3 matrix that looks like this. So basically any array of 2 by 3 and mathematical objects. And the dimension can change. All the examples that I gave first are 2 by 3. Now, this discussion, so these were examples. Then the next part is let's discuss the general representation of a matrix. Normally, when we're trying to explain facts about matrices or things that are always true about matrices, we don't want to give a specific example. Back in the day, we used variables, we used different methods of showing or parameters to generalize something. For matrices, we usually generalize with either capital letter A, B, C, D, E, or the other option is, and it could be used in conjunction with the capital letter. The next representation, which is usually we use bracket, lowercase, I and J. I and J shows where I shows what row we're at, J shows what column we're at most of the times. And then, or at least for the representation, I should say. And then the other method is just packing up with the lowercase of whatever uppercase capital letter we used over here, and then putting indices on it. If you notice, let's write it up here. Let's say I'm trying to show a general 3 by 2 matrix. Then I can either show A and write 3 by 2, or show Aij and write 3 by 2. There are other methods of showing 3 by 2 also. Or I can show this way: lowercase, 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 lowercase. That's 3 by 2. The first index shows the row. For these is 1. For this one is 2. For this one is 3. And then the second index shows the column. This one's 1, 1, 1. This one is 2, 2, 2. So this is all of these are general representation of the matrix A. That is a 3 by 2 matrix. One more thing, when you're using the general representation, depends on what you're trying to establish in your statement. You either use this or this or this or all of them. So that's why we give you all the options. And so what is up with the dot, dot, dot? In here, I gave you a 3 by 2 matrix, and it was easy to put in all this. There will be 6 entries. Entry 1, 1, entry 1, 2, no, entry 2, 1, entry 2, 2, entry 3, 1, entry 3, 2. Sometimes we want to be more general. We don't even give the dimension of the matrix. And that's an example of it. So if I tell you a general, show a general M by N matrix, so you start writing it up, and you put indices in there. And then you don't know how many is N. So you kind of put a few dots in there to show that I don't know how many there are, but I will end up at the entry 1N. And then again, when you're going downward, you know that there's A21 underneath A11, and also know there's A22 underneath. And then you kind of get tired of writing it up. So you write 2, 3, and then you end up with 2n. And also this way. And I know the last row is the mth row. So I go M1, AM2, AM3, and AMN. To be consistent, I have to have the bracket ending down here. So that's the general form of matrices, and we come back to this and when we get through matrix operation, I kind of want to go back to this general format and show you a few things. Now, what is the next step? Matrix operations. So what is matrix operations? What are matrix operations? I'm sorry. So what we have written down here, sum and difference of two matrices is an operation that can be defined. Scalar multiplication is another operation that can be defined. And there's matrix multiplication also can be defined. What I want to do is first to go through sum and difference and scalar multiplication, and then explain to you what identity matrix and zero matrix is. And the last thing that I do in this video, I'm going to explain matrix multiplication. So go back to the first operation I want to define. Let's define sum and difference. Okay. For sum and difference, you can take, operation needs at least two objects, and so we have to have two matrices. Is there a relationship between the two matrices? They have to be, for sum and difference, they have to have the same size. So for example, you can add these two matrices, but you cannot add these two matrices. Why? Because the first one is a 2 by 2, the second one is a 2 by 2 in here. Both sizes are the same. This one is 2 by 3, and this one is 2 by 2. And the number of columns in the first one and the down below is not the same as the number of columns in the second one, in the second set. So this is not defined. How do I define this one now? Now that we decided the size of a matrix matters, and we decided that these two can add up, how do I add these two up? So this is how it goes. You go to the same entries. This is entry 1, 1, adds up to entry 1, 1, and it goes to entry 1, 1. This is entry 1, 2, entry 1, 2. They add up together and they go into entry 1, 2. This is entry 2, 1, entry 2, 1. They add up together and they go to entry 2, 1. And then the last one, entry 2, 2, adds up to entry 2, 2, and it goes in here. And then I can, when I write 2 plus 1, it's just entry 1, 1. That one is just entry 1, 2, and so on and so forth. So when I add them together, 3 in here, 1 in there, 3, 9. Now I'm going to erase the board and continue with sum and differences and scalar multiplication. So let's continue with sum and matrix operations and sum and differences of two matrices. Let's say I want to show the sum and difference for 2 times 3 matrices. And so the general matrices, let's say matrix A and matrix B. Another way of representing this is, and I know both of them are 2 by 3, so I can show A1, 1, A1, 2, A1, 3, because 3 columns, A2, 1, A2, 2, A2, 3. And then for matrix B, I can show B1, 1, B1, 2, B1, 3, B2, 1, B2, 2, B2, 3. And if I add them together, then the resulting matrix should be the same entries add together, and they go in the same entry place. The same entries 1, 1 go add together, and they go to entry 1, 1. Entry 1, 2. And so that's a representation of just about any 2 by 3 matrices added together. Now, if I want to change and make this a subtraction, let's say instead of addition, I like to have a subtraction. So matrix A minus matrix B. In that case, entry A1, 1 minus B1, 1 goes to the resulting 1, 1 entry. Entry 1, 2 minus B1, 2 goes to this resulting. And so everything changes to a negative sign. So in this case, matrix A minus matrix B looks like that. Example, let's give one example of subtraction, and then we move on to scalar multiplication. So subtraction, we gave an example for for addition. Now subtraction. Let's subtract 1, 2, 3 from and notice again, both multiplication, both sum and difference for both of the operations, the two matrices have to have the same dimension. In this case, both of them have 2 rows and 3 columns, and 2 rows and 3 columns. So this is a 2 by 3, this one is a 2 by 3, and we're on the right path. So subtraction again, that minus this, which is -2, goes to the first one. Then I go, then 2 minus 5 goes to the second column of the first row. Then 3 minus 6 goes to that one. And then let's say 5 minus 1 goes to this one. 7 minus 0 goes to that one. And then the last one is 5 minus 1, which is 4, and goes to that one. Okay, so we're done with the sum and difference of two matrices. But I want to do one more notation thing. Sometimes if you don't know the dimension of the matrix, rather than writing it this way with all the indices given, you use the other representation of the matrix. So if I have A and B are M by N matrices, then I can write it this way. I can write Aij plus Bij, and underneath I can write M times N is equal to, each entry Ij has to add to entry Ij, goes to entry Ij in here. So I can write it like that. So now we're done with this part of the lessons. Let's start with scalar multiplication. I'm going to erase the board and come back. So we want to continue with scalar multiplication. Scalar multiplication. When we talk about scalar multiplication, we're talking about something that is not a matrix multiplying by the matrix. For a starter, that something is always a number. But more generally, it's not an array of numbers. It's just one thing. In future, you can see that you can multiply a matrix, scale multiplication, by a function, or as long as it's not an array of functions, or a pair, or a vector, or anything like that. That's called scalar multiplication. So at this point, if I'm saying number, I'm saying that a constant with a matrix A, and an n by n matrix, I'm sorry. Let's start with an m by n matrix A, and a constant. C, then, or a real number C, then C times A is equal to C times AIJ. That's CAIJ. So basically, I multiply every entry in the matrix by that constant or that number or whatever else that you have in mind. So the next thing that I want to discuss is, the example of this one. I'm sorry. Example. Let A be 2, 3, 5, 6, 7, 8. Find 3A. Okay. So in this case, I have to multiply each entry. 3 times 2, 6. 3 times 3, 9. 3 times 5, it's the entry 2, 1 goes in 2, 1. 3 times 6, entry 2, 2 goes into entry 2, 2. 3 times 7, 3 times 8, and this is the resulting matrix. Something that you notice, if it's the true scalar multiplication, you have a scalar, you multiply it by the matrix, it's always possible. So that does not is not defined, does not work in here unless if it's scalar multiplication. The other thing to notice is that really scalar multiplication is scaling the matrix. You're making every entry, you're multiplying every entry, you're making the matrix that much bigger all around. And so literally for some of the future work with matrices, you notice that everything kind of blows up or gets smaller with the same factor. And so that's something that comes in handy when you're doing transformations and so forth. The next thing that I wanted to discuss is the identity matrix and the zero matrix. And I'm going to take a little space in here and first explain the zero matrix. So what is a zero matrix? Zero matrix, we have to have a dimension for it. Let's say a 2 by 3 zero matrix is, here's an example, 0, 0, 0, 2 rows, 3 columns, and it looks like this. The beauty of zero matrix is if you want to create a zero matrix, you multiply any matrix of that size by number 0. So I can, this also is equal to scalar multiplication of 0 times that matrix. What else about it? And so zero matrix, when you add, the other way of showing zero matrix is this. So with a capital letter O and m by n underneath it. Or, and this means that in m by n matrix, which all entries are 0. Then the last thing that I want to say is that any matrix added or subtracted with zero matrix gives the matrix that you started with. So this is the identity of addition for matrices. And we come back and we discuss the identity matrix. So the last piece that we want to cover about matrices before we start the matrix multiplication is the identity matrix. What is identity matrix? Usually we show it with a capital I and then a number n on the bottom. Why one number? Because it's a square matrix. Let's start with an example. I3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. What is that? That's number 1 on the main diagonal and 0 everywhere else. And for example, I4 is going to be 1, 1, 1, 1, and 0 everywhere else. And so on and so forth. So if I want to write the general format, I have to write 1, 1, a few dots, and then 1 at the end, 0, 0, a few dots, and 0 at the end, and 0, and then 0 in here, 0 in here, and so that main diagonal and our ones everywhere else is 0. So identity matrix has this property with the matrix with matrix multiplication, and we come back to it after we discuss the matrix multiplication. And so that will be the next video.